No worries, man. Not a big deal. All right, well, welcome to our March 5th lab. So today, we don't have very much to do actually, so it'll probably be a pretty quick lab. We're just gonna run through the steps of how to conduct a Wilcoxon signed rank test in SPSS. So we're gonna use the dataset parentchild.sav. Okay, so this dataset is available on the course website. And it looks like what follows. Okay, so you can see that we have 20 observations here. We have what we are measuring is the amount of time an individual spends texting their parent, and then the amount of time the parent spends texting their individual in a typical week while that student is at university. So we have, for example, in the first observation, this child or the son or daughter of the parent spent 45 minutes texting their parent. The parent spent 40 minutes texting them. And then we have the difference between the scores given in the third column. So the question here is essentially, is there evidence that the amount of time that the child spent texting their parent is different from the amount of time the parent spent texting their child? So we're going to use this particular data set to illustrate the Wilcoxon rank sum test. So the Wilcoxon rank sum test is an alternative to the paired two-sample t-test. So the assumptions that we make here are: one, simple random sample was collected, and two, distribution of variable of interest is symmetric. Okay, so for the first example, it's actually told to us in the materials that this is a simple random sample. So we can say, yes, this is indicated in the lab or in the description of the problem. Now for the second assumption, all we have to do is verify normality or verify symmetry. And we're interested in working with the column of differences here. So there's a number of ways that we could verify symmetry. For example, we could use a box plot. So if we do box plot, simple, variable here, options, category axis. Wait. Oh, can I not do a box plot for summaries of separate variables? There we go. So we go box, legacy diagrams, box plot, summary of separate variables. Click OK. Okay, so here's our box plot. So we're going to take this now. All right, I'm going to insert this below. Right, and then we could also do things like construct a histogram in this place. In this case, so we can go graphs, legacy dialog, histogram, variables difference, click OK. Okay, so these are two natural tools for checking for symmetry. So now we can say, based off the histogram and box plot, there is evidence that the variable of interest, which is the differences between measures, is symmetric. Or that the distribution, sorry. So again, with the signed rank test, effectively what we are doing is we are removing the requirement for the normality procedure. So this particular test, we can utilize this when we don't necessarily have evidence for normality. Now, as it turns out, if you actually check to see if there is evidence for normality for the differences in this case, I think it does work out pretty well. So we can just take a look at that. So generalized linear models, sorry, this would be descriptives, QQ plots. Let's take a look at this thing here. So you can see that it's actually pretty close to the line, but we do have a little bit of like an S-type shape. So if we were being really strict, we might say that this gives evidence of heavier tails than what we would normally expect. And if we do look at the histogram, for example, we can very clearly see here that this is not a normally shaped histogram, right? So we have evidence that the tails are a bit heavier than they should be in the case of normality. And then we also can see from the histogram that it's clearly not a bell curve shape. So that the normality assumption, it's probably reasonable to say that we can't verify it for this particular data set. So that's another reason why we need to use this Wilcoxon rank sum test, because we can't rely on the normality assumption, which we need for the student, for the paired student t-test. Okay, so performing the Wilcoxon rank sum test in SPSS is pretty straightforward. So first off, we start off with our assumptions. So we have H, 0, and then we're going to have eta 1, because we're talking about the difference between two populations. So we can do this as eta 1 not equal to, or equal to eta 2 in this case. So we're going to insert single . Okay, so we have eta 1 equals eta 2 versus A, eta 1 not equal to eta 2. Right. And now we will test at the 5% significance level. Okay, now we have to find our test statistic. So this is where SPSS would come into play. Okay, so in this data set, we actually have 20 values. Now the way that SPSS works is when you run the Wilcoxon rank sum test, it actually provides you with an approximation to the test statistic based off of the standard normal distribution. Okay, so to run the Wilcoxon rank sum test, we go analyze non-parametric tests, and then we go legacy dialogues to related samples. Now we take the pair, which is child versus parent, test type equals Wilcoxon. We have some different options here. Okay, don't need to check any of those, and we click OK. And here's our outputs. Okay, so if we consider the first table, what we have here is, so from table 1, we can say the test statistic, which is W0, is equal to the sum of the positive ranks, which is 141.5. All right, now, unfortunately, one of the issues that we run into here is we don't have a p-value or a critical value that's directly given to us. So for this particular test, what we could do is use the Wilcoxon rank sum table that's introduced in the lectures. So if we wanted to do that, and we wanted to compare directly to the test statistic that we found from this table, we would have the following. So we would have, on step 4, if we opened up our rank sum table, which I'm going to just pull up in a moment here. Okay. All right, so here is our rank sum table. So we have 20 observations. Okay, we're testing at the 5% significance level, but it's a two-tailed test. So here is our upper critical value, 158. So if we take the critical value approach, we have W subscript 0.025 equals 158. And using the rules that we established in lecture, we would then have W 0.975, which is the lower tail bound, equals the sum of all the ranks. So that's going to be 20 times 21. Okay, over 2, which is equal to minus the lower bound. So this is going to be 210 minus 158 equals 52. So then we can say, since test statistic is between and okay, we do not reject H0. Okay. And then if we wanted to, and if we wanted to take the p-value approach, okay, so actually I'll write this as using Wilcoxon rank sum table. So if we took the p-value approach now, Okay, so if we go back to our rank sum table, we have 20, we have 20, a sample size of 20. We have a test statistic of 141.5. So 141.5 is in between 140 and 151, which means that the p-value in the upper tail is between 0.1 and 0.05. So now we can say, since the probability W is greater than 141.5 is less than 0.1, since 0.05 is less than the probability that W is greater than 0.01 is less than 0.1, then the p-value, then 0.1 is less than the p-value is less than 0.2. So therefore, on step 5, if we use the Wilcoxon rank sum table, we do not reject H0. Okay, so that's one approach. Now, the other thing that we can consider here is that we have a sample size of 20. So since we have a sample size of 20, we can also take an approximation based off the normal distribution. So step 3, okay. So I'll just write this as compute test statistic using standard normal approximation. Now this value is given to us directly in the SPSS output. So you'll notice that below the Wilcoxon rank sign test table, we have a second table which gives the approximation based off a z-score, or the approximation based off the standard normal distribution, and it gives the p-value for that test. Okay. So if we insert picture from file, right, we have the following. So that means that our test statistic here is negative 1.874. Okay, so then on step 4, we can see that the p-value for this test is going to be equal to 0.061 over 2, which is 0.0305. So then on step 5, we would reject H0 based off of this approximation. Oh no, sorry, this is a two-tailed test. I don't need to divide. Okay, so again, do not reject H0. So we actually have agreement in results. So based off both tests, we can say at the 5% significance level, the data do not provide sufficient evidence to suggest that the median amount of time that children spend texting their parents per week while at university differs from the median amount of time parents spend texting their children per week while at university. All right, and that's it actually. So that's how you work through a Wilcoxon rank sum test for paired data using SPSS. Again, the output from SPSS gives us two options. So we can take the direct approach where we use the Wilcoxon rank sum values as we learned about them in lecture, or as you have learned about them in your specific lecture. Or we can use the approximation based off of the standard normal table or the standard normal distribution. Again, the approximation based off the standard normal distribution, this works. We use the rule of thumb n greater than or equal to 15 to employ this. So when we have a sample size that's larger than, or a sample size that is at least 15, that's when we typically say that this approximation is valid. But if we do not meet that requirement, then typically we would take the direct approach. All right. So that's it for the material that I wanted to show today. Next week, we're going to do Kruskal-Wallis test and the Wilcoxon rank sum test. Do you guys have any questions? Okay, well, if there's no questions, then I will open up the rest of the period to like a work session. And if you guys have any questions, I'll be hanging around. And otherwise, have a good weekend, and I'll talk to you guys next week.